Problem set number 3, question number 4 with heart rates. So part A asks you to compare the observed frequencies to expected frequencies, given a mean, a standard deviation, and an assumption of normality. Now, contrary to the answers that some people gave, when this question talks about normality, it's not asking whether or not the patients are normal. We're not saying anything about any of the patients having weight problems or if they smoke or don't smoke. That's well outside the scope of both what the class talks about as well as what we can infer from the data. Really, this question focuses on whether or not the distribution of the data are normal. Do the data follow a normal distribution? As if it did, then we can do things with statistics. And if the data are not normally distributed, then there are things that we should not be doing with our data. So part A is asking whether or not the distribution was normal, or at least leading up to that question, by comparing, again, the observed frequencies to expected frequencies. There are different ways you could do this. I will show you the way that I ended up doing it. Here we have the given table. So there's our heart rate categories. There's the observed frequencies. We wanted this expected count using the properties of the normal curve. So the way I did it was to take the first category and calculate the probability that an individual from this sample would have a heart rate less than 60 given a mean of 70, a standard deviation of 6, and that there were 8,922 patients. So all of this data was given directly in the question, and the key to answering part A was to use the properties of the normal curve to come up with this particular probability, or something like it. So to solve that, we use, at least to solve that using Excel, we use the norm.dist function, and we plug in our values. 60 is the cutoff that I'm interested in, 70 is my sample mean with a standard deviation of 6, and for all things normal curve related, we use the true flag, at least as far as these Excel functions go. And we plug that in, we see we get a probability of about 5%. Ultimately, I want a count, not a probability, so I take that probability, or that proportion, if you will, and multiply it by my total sample size, and that gives me an estimated, an expected number of people. And I can compare that to the actual that comes from this table, or from the given table. We can then repeat that for different thresholds. So a second threshold identified as 70, so it's kind of the upper boundary of this one. So the probability of a patient having a heart rate less than 70 follows a very similar syntax, a very similar formula. Norm.dist, there's my 70, that is my cutoff. 70, that is my mean. The standard deviation, the same true. Because my cutoff is equal to the mean, and the mean, by definition, for a normal curve, is right in the middle of the data set, then 50% of my population has to be lower and 50% has to be greater. And that is what shows up here. So I take that 50%, multiply it by my sample size, and I get an estimated number of people. There's my actual, and notice this actual is not in the table, because the table is between 60 and 69, and I am looking for less than 70. So the way I'm doing this, I'm actually using a cumulative sum of the categories. If you wanted to, you could run these same calculations for those categories separately. So this first one would still be the same, less than 60. But the second probability that you calculated could be the probability of someone between 60 and 69, or between 60 and 70. And so you would do this probability of less than 70 minus the probability of less than 60. And that difference would tell you the probability between 69 and 60, or 70 and 60, depending how you did it. And then if you did it that difference approach, so the probability of 69 minus the probability of 60, you could still get an expected value, and the actual value here would be the same. You would use the same one as the original table. So either way, they'll end up giving you very similar answers for part B. So part A, we get our numbers. That's really all I wanted. Part B says, well, given the actual numbers and the expected numbers, is it okay to use the normal curve? Like, are the data normally distributed? Uh, you might be able to look at the table and say, well, there's a bit of skew in here, but well, at this point, we know how to use a chi-square distribution to directly test whether or not observed data match expected data. We did not know about chi-squared tests at the time, so really the best thing that we could do, and certainly better than just eyeballing a frequency table, is to make a plot. And so we make a scatter plot of the estimated data on one side and the actual on the other. You could flip these two around, doesn't really matter. Ultimately, we're looking for a straight line. And if the data points do make a straight line, then yeah, the assumption of normality is pretty good. A straight line means that our estimated counts are following our actual counts, and so the actual is following our theory. Our theory is that the data are normally distributed. If actual follows that, then great. Our data are actually normally distributed, or good enough. So answer to part B, yeah, this is nearly a straight line. So normality probably is a decent assumption to use. In part C, we're asking for the probability of patients having greater than 70. Well, 70 is the mean. A normal distribution is symmetrical, so the mean has to be right in the middle. So we know just from that 50% of the population has to be less than and 50% has to be greater than the mean. So probability is 0.5. We could also use the norm.dist function like we did up here. Here I use the complement. So lots of different ways to do it, but 50% is the correct answer. In part D, we're asking for the same kind of thing, the probability of patients that use the beta blockers greater than 70. So beta blockers had a slightly different mean, a slightly different standard deviation, and a slightly smaller sample size. Here, because the value we're looking for, the cutoff, 70, is not equal to the mean. Our probability is not going to be equal to 0.5. We have to use an actual function for this. So our general function for a probabilities has the .dist ending. So we're using the norm.dist. There's our cutoff. There's our sample mean, our sample standard deviation. The norm.dist gives us the left-hand side of the curve, so kind of the less than a cutoff. We want a greater than, so we need to use the complement. We need the other side of the curve. So that ends up being 45%. We'll do the exact same kind of thing for the probability of non-beta block users. We look at our formula here, it's still norm.dist. There's our cutoff, our new sample mean, new sample standard deviation. This just this part would give us the left-hand side of the curve, the less than 70. We want a greater than 70, so we'll take the complement, 1 minus that, and see that it is about 65%. And the difference between the two is literally the difference between the two. It is 0.65 minus 0.45 is about 0.2. And that is that.